Here I'd like to add some more detail about the comparison between electromagnetic waves, light, mechanical oscillations. There's a lot going on in this diagram, but let me just kind of walk you through it. In this column, I have a mass on a spring. Here's a pendulum, and then here's an LC circuit, and then over here we're going to be building up a wave. To start off, a mass on a spring oscillating, you either pull it out or compress it. So if I fully compress the mass on the spring, all the energy is stored, or it's potential energy. And so the spring is going to push the mass that way. For an oscillator, for a pendulum, if I pull the pendulum up and then let it begin swinging, here all the mass is stored, but it's stored as gravitational potential energy. Spring potential energy, gravitational potential energy. For an LC circuit, this is an electromagnetic oscillator. Quite simply, we have a capacitor and an inductor. Two plates with charges, and you connect them by a coil of wire. Coil of wire, essentially you're making just a short circuit between the plates. If I charge the capacitor, initially all the energy is stored in the electric field. Once I complete this circuit, once I include the inductor, current is going to begin to flow. So here's stored energy in a spring, gravity, and then stored energy in an electric field. If I release the mass on the spring, it'll begin moving. The force will push it this way. The speed's going this way. If I release the pendulum, it'll begin moving. The ball begin to swing down toward equilibrium, but it's still got some potential energy. In the case of the LC circuit, electric current begins to flow around the circuit. It'll begin to flow around here and here. As that happens, the capacitor will discharge. You'll lose the electric field. But in sending current through a coil, you're going to build up a magnetic field through the coil. And initially, that change in magnetic field is going to want to oppose change. So it'll go by self-inductance. In looking at a wave, so the intensity of a wave, initially the energy is, the kinetic energy is, the energy is stored. Here, as it begins moving, the intensity of the wave goes up a little bit. At some point, the mass on the spring will reach equilibrium, and so here, at this very instant, the spring isn't exerting a force in either direction, and we're at a maximum speed. This is the fastest that the mass on the spring can be moving as it crosses equilibrium. In the case of the pendulum, as the pendulum swings through equilibrium, this is the fastest it can be moving. LC circuit, here the capacitor is completely discharged, and the current, for at least an instant, is a maximum value. And as a result, we have a maximum value of magnetic field through the inductor. And so our wave will reach a peak. Now, looking at sort of the last two drawings I have in the diagram, as the spring passes, as the mass on the spring passes equilibrium, it'll keep going. Its momentum keeps it going forward, and it'll go past equilibrium. Here it's moving with some speed, but the spring is pulling back on it. Pendulum, same thing. It moves with maximum speed through equilibrium. Momentum keeps pulling it up, but force is pulling it back down. In the case of the RLC circuit, the inductor works to recharge the capacitor, but to charge it in the other direction. So you'll build up positive charge on one side, negative charge on the other side, and as this happens, the current flow will still flow, but it'll be decreasing. And so you still have some magnetic field, but not quite as much as what you had before. The current, the magnetic field in this analogy can kind of like moving charges. Moving charges kind of like the moving masses in a mechanical oscillator. Finally, the last step, I forget to draw the wave, so the wave begins coming back down, but still moving a little bit. In the mass on the spring, at some point the momentum will carry the mass as far as it can go, where it'll come to a stop, and the spring will begin pulling it backward. The pendulum will swing as far as it can go until it comes to a stop, and gravity begins pushing it back downward. In the RLC circuit, at some point the capacitor becomes as charged up as it possibly can. And at this point, no more current is flowing, at least for an instant. So here again, all the charge is built up on the capacitor. All the energy is stored in the electric field, and there's nothing stored in the magnetic field. These are oscillating systems, and so ideally these will bounce back and forth at the different rates that we showed a minute ago. And so this will begin moving this way, and the pattern will turn over, oscillate with the periods and the frequencies that we just showed. So the analogy for the LC circuit is that you have stored energy in the electric field, and momentum is essentially associated with current and the magnetic field. And as a reminder, you have a resonant frequency for the RLC circuit 1 over square root of LC, where L is the inductance, properties of the coil, C is the capacitance, and these are properties of the capacitor. As we saw in the last set of diagrams, the LC circuit is an oscillator, but this oscillator works for electromagnetic waves. So what kind of waves are these sending or receiving? And the answer to that is radio waves. This is the guts or the heart of really any radio transmitter or receiver. So a very simple circuit. You start off with a charged up capacitor. You hook that up to an inductor. And then there's some additional stuff to hook up to get a speaker, antenna, that kind of thing. But again, this is the heart of it. If you've ever hooked up a crystal radio, you know that it's fairly simple. So the energy is stored here in the capacitor in an electric field initially, but we have a simple coil of wire. This is essentially a short circuit, so once this is connected, current begins to flow. As current begins to flow, the capacitor begins to discharge, and the inductor builds up a magnetic field. The magnetic field has similar to momentum. It'll begin pushing charges kind of around. So for at least an instant. current will reach a maximum value as the capacitor becomes completely discharged. Capacitor's completely discharged and the magnetic field reaches a maximum. Kind of like what we saw with the mass on the spring and the pendulum. This isn't a stopping point. It still has some essentially the same as momentum, and you'll begin charging up the plates of the capacitor in the other direction and build up an electric field the other way. And as that happens, the current will drop down to lower and lower values, essentially to zero. And as a result, the magnetic field will decrease for an instant. And it'll oscillate back and forth between these two conditions, a maximum electric field and a maximum magnetic field. Now, how does this transmit or receive radio waves? Typically, the antenna is attached here to the capacitor, and so you can imagine the antenna as taking the capacitor plates and taking them out and just sort of bending them out, stretching them. And so as this oscillates, your electric field starts off this way between the capacitor plates, and actually begins to kind of turn into plane waves that are emitted by the antenna. These are planes or sheets of the electric field. Another thing that happens is as electric field changes, you induce a magnetic field in the opposite direction. So perpendicular here, we induce a magnetic field that encircles the capacitor and essentially encircles the plane waves. Likewise, a similar thing is happening with the inductor as the magnetic field changes back and forth. In the inductor, you induce an electric field that surrounds the inductor. And so by this mechanism, this will emit and receive radio waves. The frequency of the radio waves depends on L and C, the inductance and the capacitance. Here the frequency refers to, if you want to tune your radio to a particular station, the frequency is the station that you're listening to. Modern radio, it's not quite this simple, but this is the tuner for an old radio. So as you turn the dial, you're actually moving plates and physically changing the capacitance as these metal plates overlap.